Please.
There is a thing that we do, and the details vary from language to language, but in Ruby it often looks something like this. You realize that this bit of code over here and that bit of code over there are basically doing the same thing, except they're implemented differently. So you decide to switch everything over to use just one of them, and about 17 tests break. And you remember that there's an edge case, so you quickly patch a conditional. Now 24 tests are failing. And you realize that there's a missing dependency, so you pull that in, and now you have about 50 failing tests, and it turns out that there is a conflict between two different dependencies, so you swap them around so that they load in the opposite order, because Ruby. And now almost 80 tests are failing, and then apparently there's an encoding thing that has gone haywire again, assuming UTF-8, but then actually you're getting Latin 1. Or is it the reverse? I don't know. And the method you're trying to use needs access to some stuff that's not in the public API, so you figure, whatever, I'll just use send. And a whole bunch of stuff blows up, and it's something to do with unexpected nils. And it's been hours since the tests were last passing, and now you're considering monkey patching nil class. And instead, you do a get reset hard. Now, I think every single programmer I know has done some version of this. And not just once, either. We keep doing it. It's as though the fix is right there, within reach. It's so close we can practically taste it. And we chase after it, and our vision narrows, and whatever original plan we had is long forgotten. And this is messy, and it's frustrating, and it's massively wasteful. And it doesn't have to be that way. So I'm going to talk about the underlying principles of how to avoid that sort of train wreck. Now, to talk about this, I'm going to use some code that generates a children's song. The song is very simple, but it has an algorithmic component, and this adds just enough complexity to demonstrate real-world refactoring principles without bogging you down in real-world code. So, to start off, the whole code example is all just text. Now, the code is actually short enough to fit on a single slide, kind of. The entire text of the song is hard-coded into a here doc, and this is wrapped in a method, which in turn is wrapped in a class, and that's it. Right? This code is actually really nice. It's short, right? It's very easy to read. It does exactly what it needs to do. And you might be wondering how we're going to talk about refactoring when the code is so simple. And that is an excellent question. Usually refactoring is about taking a mess and cleaning it up, which might make it seem like refactoring is about aesthetics. But fundamentally, refactoring is not about beautiful code. Sometimes refactoring could be about comprehension. You might refactor something in order to be able to understand it. But that raises the question, why do you need to understand it? If you have horrible, awful, terrible, no good code that you don't understand, but it does exactly what you need to do, just leave it in production. Walk away. The right time to refactor is when we need to achieve some practical purpose. You need to make a change, and that change is hard to make the way that the code is now. So if we don't refactor, then we would make a change in a way that is going to cause pain and suffering, which we don't want. So looking at our simple, understandable, perfectly working code, why would we refactor? Well, it turns out the code used to do exactly what it needed to do. It generates the age-old tale of a little old lady who inexplicably swallows a fly and then compounds the problem by swallowing larger and larger creatures until it kills her. Now, though, there's been a change in requirements. We want to create variations of the song. It needs to be basically the same song. It's the same algorithm, but with different data. We need to be able to swap out the original animals with arbitrary creatures, and while the code that generates this song is simple and understandable, it will not let us do that. So we'll refactor. Now you might be tempted to just look at the song and write something from scratch that satisfies the new requirements. And this tends to not work as well as people would like it to. So here's the thing, the code works. One of the variations that we want is the original version of the song. So the code we have contains the correct algorithm, and we need this. It just has to be a little bit more flexible. So it's a really good starting point for a refactoring. Now, notice that we don't have tests for obvious reasons, right? This code is so simple that there was no point in adding tests. And now we're going to be changing things. So we need a quick and reliable way to make sure that we're not heading off into the weeds. So I'm going to make a very simple test, the simplest that I possibly can, by copying the here doc into a brand new test, and then I'll stick the output in a local variable and assert that this is identical to the generated lyrics, which obviously it is, because right now the expected output is an exact duplicate of the production code. So this type of test is called a characterization test, and it usually won't be an exact copy of the production code, but the main idea is that you're creating a test that asserts that whatever is there is correct. Whatever the code is doing right now is exactly what you want. So we have some code, we need to change it, we have tests, so we can get started. The first step of a refactoring is almost always to just look at the code for a little bit. Now, you'll rarely have some blinding insight that will tell you exactly what to do, but very often you'll make some observations about what's hurting your ability to make the change that you need to make. And in this case, the most striking thing about this code is that the song is algorithmic, but there is no algorithm apparent in this implementation. At a very high level, this algorithm that we can't see is doing a couple of things. It tells us how to construct a verse, and it also tells us how to string those verses together. So that's not a very fine-grained way of looking at it, but it does help break the problem down into a task that is a little bit more manageable. So first, we're going to deal with individual verses, and then we're going to look at how to string them together in the right order. And then once that's done, it should be fairly easy to see what needs to be done to add support for the new requirement. Now, right now, I can't really tackle the first to-do here because the current implementation is just a pile of text. It's all the verses, all of the time. And I can't get at any single verse by itself. So before I even get started, I'm going to break the here doc up to make individual verses accessible. And for that, I'm going to use a case statement with one branch for each verse. And then I'm going to loop over the range of verses and join them to get the full lyrics. And because I want to be able to focus on the verse all by itself, I'm going to go one step further and then extract this case statement into its own method. So this change is a little bit tedious, but it's very quick and it's very straightforward. And we end up with individual verses that look like this. So it's lots of strings and they're all concatenated together. Some of this text is algorithm and some of this text is data. And the thing that bugs me the most here is that the algorithm and the data are all mixed together. So to get a better idea of what the algorithm actually looks like, I want a better separation of the static and the variable parts. And I'm not really interested in naming things yet. So I'm going to use the C-style string formatting, which gives a really nice delineation with the static stuff on one side and then all the data on the other. So this is a really small change, but it is noticeable even when squinting at it. This is the here doc that we started out with, and then we used a case statement to break up the individual verses with all the strings unchanged. And then now we've dissected this, all of these strings in place to separate the template from the data. Now, you might argue that I just shoved code around on the slide and pretended to have refactored the way that some people shove food around on their plate and pretend to have eaten, right? It's kind of pointless to make such a small change. But the goal was to bring the algorithm a little bit more into focus. And this tiny change definitely did that. Now there's an algorithmic component that virtually jumps off the page. Every verse grows systematically. It adds repetitions, and then it stops abruptly. So I want to explore this a little bit, and I want to do it without risking the code that I know is working. I just want to write down this little bit of algorithm that I think I'm seeing without using it yet, so that I can figure out if it makes sense. So most of the verses take this phrase, they repeat it some number of times, passes in a variety of different creatures each time. This is not a lot of code, but it is a key element in this algorithm. It seems like a complete thought. And when something in the code feels coherent and solid like this, I think it's worth making an attempt at naming it. So this particular part of the song is trying to explain the reasoning behind the little old lady's behavior. It's talking about why she would ever do such a thing as swallow a bird or a dog or a goat. In other words, it's talking about her motivation. Now we need to call this method some number of times, each time with different data. And this is another little piece of the algorithm revealing itself. Now ignore for a moment that cows and goats don't actually eat meat. And notice that the predator in one verse becomes the prey in the next. We essentially have the same list hard-coded twice. But algorithmically, it should just be one list. And this, too, is a core concept in the song's algorithm, so we should give it a name. Notice the order of the animals here. This is not the order of the verses. The natural order of the algorithm, based on how it lives in the code, is the order of predation. It's who eats whom. So now our experimental bit of algorithm looks like this. It takes the two concepts that we've already named, critters and motivation, and it combines them into a bigger story. All of these critters are taking part in a larger drama where each successive iteration through the loop intensifies and exaggerates the poor little old lady's discomfort. Now this chunk of code also needs a name. Here we're talking about a sequence or chain of events that describe a sort of bizarre food chain. There's a trade-off here. We've taken something that was blindingly simple, and we've complicated it. And we've paid a price, but we've gained something important in return. Our mindless simplicity was hiding information. And the complexity, on the other hand, is revealing the bones of the algorithm. So remember, I've not actually used the code anywhere. I've been doing all of this experimentation as a parallel implementation, just to see what it might look like. And now I feel ready to swap it into the actual code. So this is the first place where the algorithmic bit occurs. Here we're in verse 2. If you swap out this line with a call to the chain method, the test blew up. And that's because it generates the entire chain, not just the line that we need. So when my test's failing during a refactoring, the first thing that I do is I undo my change to get the tests back to green. And this might seem a little bit odd to you. It's obvious what's wrong, right? I could just fix it. Why undo? So here's the thing. I think I know exactly what went wrong. But I've been wrong about what I think is wrong so many times. And when you're right about what's wrong, it's fine. Then it just, moves on. But as soon as the first fix doesn't actually fix the problem, that's how you get sucked into that rabbit hole that ends with a git reset hard hours later. So some people have a rule, that goes like this. Their tests cannot fail twice in a row. But I'm kind of lazy, so I don't bother counting. So if it blows up, I just back it out. That way, if the fire alarm goes off, or if someone calls me with an urgent request, or if I get this need to go to the beach for the rest of the day, when I have backed out, I know my code is running. I know I could deploy to production at a moment's notice, and I would be safe to do so. When your refactoring steps are really small, like the ones that we just took, it doesn't really hurt to throw away the change. Like usually you're just throwing away a few seconds of work, maybe a few minutes at the very most. So it doesn't even feel wasted because you'll have learned something from that change, something that gives you a better idea of a better change to make. So back in the code, the problem is that I forgot that we don't need the chain with all the critters in all of the verses. We just need the critters that we've introduced so far in the song. So now when we call the chain in verse 2, the tests pass. So let's look at verse 3. Swapping in chain here fails. It turns out that the chain is generating this sequence of events, which seemed right to me when I wrote it, but actually the original version of the song always throws on some extra commentary when it talks about the spider. And it does this for every single verse where it describes the bird catching the spider. So back that change out, get the test suite back to green, and let's rethink this. One part of the chain is not like the rest. What you'll usually see in most code bases when you have a rule with an exception is a conditional. Now, most advice tells you to avoid conditionals, and that's really good advice because conditionals have a tendency to breed. You start with one, things lead to, and one thing leads to another. Eventually, somebody's going to get hurt, but it's not really immediately clear what we should do instead. So I'm going to lean into this conditional and then see where it takes me. There are two really important principles to keep in mind when dealing with conditionals. The first is that the conditional itself should contain the smallest possible difference. Now, this may sound obvious, but I can't tell you how often I see conditionals out in the wild that have duplication in each of the blocks. If it's the same in both blocks of an if statement, then it's not really conditional on anything. But then if we only keep the wriggly bit of the spider, then there's nothing to put in that else branch. Now, you could drop it, most people do, but that might lead you to think that you are naming just the exception, and you're not. And this is the second principle, and getting this wrong could throw your entire refactoring out of whack. A good conditional doesn't represent the exception to a rule. It represents multiple variations on the same concept. So the rule is one variation, the exception is another. It's not two different things, it's one single idea. So in the song, we're talking about the critter's distinctive features or some sort of qualifier, and it's just that some critters aren't that distinctive or special. So if you drop the else and leave only the bit about the spider, the name will almost invariably end up being about the spider. But remember that the whole point of this refactoring is to be able to swap in arbitrary creatures, so we could end up with a spider tag that returns the tag for a squirrel or a crab or a raccoon. The words that we choose are important. A name that is nonsense but temporary is totally fine. But if you have a name that feels right enough, then it's probably not going to go away anytime soon. So if you name a fragment of an idea, it introduces not only indirection, but misdirection. It's a magic trick. It gives you an illusion of understanding. And this sort of deception makes it very difficult to refactor. So by forcing yourself to consider the symmetry of the entire conditional, you're nudged in the direction of naming the whole concept. All right, so the qualifier method needs an argument. Pray is not the right name anymore. Prey is about hunting, and this has nothing to do with one animal killing another for food. It's about the critter itself. Now, this conditional feels right. Take a moment to look at it. It contains the smallest possible difference. It's symmetrical, containing both the exception and the rule. The name doesn't misinform. It's about a general concept in the song. Notice that the result of the method depends solely on the argument that is passed. Right? This method could live anywhere. Right? It could be a global function for all we care. It doesn't depend on anything to do with the song class. Now, earlier in this refactoring, we identified the concept of a critter, and each critter is a string representing the name of that critter. But now, it turns out there's more stuff associated with a critter. Right? Each one also has a qualifier. So with our qualifier method, we're trying to decorate our simple critter with more behavior. Right? The official name for this code smell is primitive obsession. And the remedy for primitive obsession is to identify the object that is struggling to get out. So our critter is not a string, it's an object. And this is the turning point for the entire refactoring. Now, suddenly, it's clear that all the variable bits of the song are associated with this critter object. We can comb through the song, find all the parts that are about an individual critter, flesh that object out, and the delightful thing is that in doing so, the conditional just vanishes. It disappears entirely. So it was useful, the conditional was useful in order to help identify the concept, but once it did, we no longer even needed it. So it turns out there are three things that a critter might have: the name of the animal, then there's the qualifier that we just identified, and finally there's a little bit of commentary from the narrator in the song, which is used in every verse for the animal that is the subject of that verse. So for the sake of refactoring, we can instantiate all the critters based on the data that we extracted, tweak the algorithm so that it uses the objects instead of the strings, and then finally, we can swap the algorithm straight into the verses. So this is the 7th verse, which is the second to last verse, and I chose it because this has the longest possible chain in it. So it should be a really good representative example of the algorithm. In the first line, we need to get the correct critter. We want the name of it. The next line is the same creature, but we're calling the commentary method on it, which I've named aside because it's shorter and this needs to fit on a slide. This time, swapping in the chain works seamlessly. And then the last line, if this will work, the last line is always the same for all the verses. It's the very last critter in the list, which is the one that started the whole cascade of trouble back in the first verse. So at the start of this whole process, in thinking about the algorithm, it felt useful to divvy it up into roughly 3 phases: how to construct a verse, how to string the verses together, and then implementing the new feature. And we've nailed the first bit. We have a great separation between the parts that remain the same and the parts that vary. Also, our code is basically stringing the verses together in the right order. We kind of got that one for free. But we can't swap in arbitrary creatures yet. And there are only 2 things getting in the way. We have a hard-coded constant with all the data in it and that the algorithm is operating on. And in several places, we have a hard-coded assumption about how many creatures there are, which might turn out to be wrong. So the hard-coded constant is a straightforward thing to deal with. So let's do that first. We're referencing it when we instantiate the creatures right here. So rather than rely on the constant, we can add a little bit of indirection by creating an initialize method and then injecting the data constant as a default value. The test will still pass. And then the caller can override it if necessary. So we need to store the data, make it available via getter method, and then refer to the stored data rather than the constant directly. And that's it for the constant. So that was 4 tiny steps. Every single step was safe. In the context of a refactoring, safe has a very precise and technical definition. A safe step is one change where the code will work both before and after the edit. In other words, if you refactor with only safe steps, the tests will pass the whole time. All right, so we've dealt with the data constant. Next, let's tackle the assumption that there are 8 creatures. So this happens in several places. The first is when we generate the lyrics for all of the verses. We create a range object that goes from 1 to 8, and then we iterate over that range. And this is straightforward to fix because we have an array of critters. We can just get the length of the array. A slightly more resistant problem is the verse method's case statement, which has a block for every verse. Now again, it has the assumption that there will always be 8 verses, that there will only ever be 8 verses. So most of these blocks are very similar. The only difference between them is that they hard code the number of verses, the number of the verse that they are on. And we happen to have a variable handy for this. It's called I. It's what the case statement is switching on in the first place. So we can use that for all of the parts of the case statement that are identical and collapse them into a single block. So the 2 remaining verses, turns out they're already identical, so we can combine those as well. And there's a fair amount of duplication between the 2 blocks, but I'm going to ignore it because I'm in the middle of dealing with something else, and I don't want to get distracted. If you read the case statement, it seems to say that if you're on verse 1 or verse 8, do one thing. If it's anything between 2 and 7, do some other thing. And what we really mean is if it's the first verse or the last verse, do one thing. Otherwise, in all other cases, do something else. And that's basically it. If we've done this right, we should be able to generate lyrics with arbitrary critter data. And the simplest way to check this is to write a small test. And when I say small, I mean as small as possible, but no smaller. The test data needs to cover all of the edge cases, everything that's relevant about the song, but it shouldn't be realistic data. If you use realistic data, it will tend to distract you from what's important. So we're not going to use lions and monkeys and lizards. We're going to use something simple and contrived and very, very boring. So with this data, we should end up with these lyrics. First and last verses are both short, the middle verses are long, and one of the middle verses has that extra qualifier. So if we stick this whole thing in a variable, we can assert that the code does the right thing, and it doesn't, which actually came as a surprise to me when I was preparing this talk. It fails because we have the wrong indefinite article. I had to look that up on Wikipedia because grammar is not my forte. It's a or an. You have all learned English, so you know this. A zebra, an alligator. Now, this doesn't seem like it's a big deal, but fixing it in a smart way actually is really difficult because English makes no sense. So I'm just going to do the naive thing, which is to put the article in the data array for both the new test and the original data. And this requires a few adjustments in the code, but it's all very straightforward, very boring, takes only a few moments. And then the new test passes. So we've successfully taken a hard-coded string and refactored it into code that reflects the underlying algorithm. The code is not perfect. It's still got annoying stuff like duplication in the case statement, or the case statement itself if you're not a fan of conditionals. And we could address those things if we wanted to, but we don't have to. Like, the code now lets us do what we need to do, and it's simple enough to understand. Kent Beck once said, "Make the change easy, then make the easy change." First refactor the code, change the structure without changing the behavior. Keep doing it until you can add your feature without hacking it in. And often you'll find that implementing that new requirement just takes a moment or two. And it kind of feels like a miracle. It turns out Kent Beck actually didn't say this. What he said was, make the change easy. Warning, this may be hard. Then make the easy change. There's exactly one thing that I hope that you will take away from this talk, and that is to take smaller steps. Your steps don't have to be as small as the ones that I took today, but a good rule of thumb is that the higher the uncertainty, the greater the risk, the smaller your step should be. And this process can feel terrifying, because when you're working in real-world code, a lot of the steps will feel like they are going in the wrong direction. You will be pulling logic all into the same place. You'll be getting rid of unhelpful abstractions along the way. You'll end up with methods that have hundreds of lines of code in them, conditionals that have dozens of branches nested many levels deep. And I would like to reassure you that this is fine. It's fine to make things worse for a little while, to help you get things under control. It's fine to implement gross workarounds temporarily if that will help you make your changes safely. Take small steps in whatever direction will get the job done. And if you do, refactoring will become delightfully boring. You will have more bandwidth to focus on the meaningful parts of your job. Thank you.